Now that we have defined what it means to multiply two matrices, it's natural to ask whether the same multiplication rules apply in this new setting that apply for regular old real numbers. So the first one we want to tackle is associativity. We use this implicitly very frequently when we multiply numbers. That says for any three real numbers, a, b, and c, if I first multiply b and c together, then multiply that by a, that's the same as multiplying a and b together, then multiplying by c. This allows us to write ABC without ambiguity, since we always get the same result no matter where we place the parentheses. So as has been the case for most of our properties, we're first going to verify that this works for C being a vector and A and B matrices. Once we understand how that works, it'll be very easy to generalize to the case where A, B, and C are matrices of the appropriate dimension. To get a feel for how this works, let's start off with an example. So A is the matrix with columns 1 minus 2, 2 minus 4. B is the matrix with columns 3, 1, 0, 3. And V is the vector with rows 1, 2. We're going to compare the products A times B multiplied by V and A multiplied by BV. So this is a great time to take a second, pause the video, and try this out yourself. So now that you've had a minute to try this out on your own, here's the solution. When we multiply A and B together, we'll get the matrix whose columns are 5, negative 10, 6, negative 12. So when we multiply the vector V by the matrix AB on the left, then we get the vector 17, negative 34. In the opposite direction, we first take the matrix B, then multiply that by V on the right. This gives us the vector 3, 7. And then we multiply that vector by A on the left. The result of this operation is the vector 17, negative 34, which is exactly the same as what we computed above. That's AB acting on the vector V. So in general, if A is an L by M matrix, B is an M by N matrix, and V is an n-dimensional vector, then the product AB acting on the vector V is the same as A acting on the vector BV. A times B is the product of an L by M matrix with an M by N matrix, so it is an L by N matrix. The vector V is n-dimensional, so AB times V is the linear combination of the n L-dimensional vectors, hence is also an L-dimensional vector. B times V is a linear combination of the n m-dimensional columns from B. So BV is also an m-dimensional vector. That means when we take the matrix A and multiply on the right by BV, this is a linear combination of m L-dimensional columns from A. So A times BV is also an L-dimensional vector. So it does make sense to say that these two things are the same, because they do in fact live in the same space. So to extend to a product of three matrices, we simply need to use that our multiplication is associative when the third object is a vector, and work column by column. Let's work an example. So we have the matrices A with columns 1 minus 2 and 2 minus 4, B with columns 3, 1 and 0, 3, C with columns 1, 2 and 3, 4. These are all three 2 by 2 matrices, So it makes sense to multiply AB and then multiply that by C to get another 2 by 2 matrix. Similarly, we can multiply B times C and then multiply that on the left by A. So take a minute, try this out on your own, see what happens. So now that you've had a minute to work on this on your own, here's the solution. So we've already computed AB above. That's the matrix with columns 5, -10, and 6, -12. So we multiply that by C on the right, we get 17, -34, and 39, -78. Going in the other order, we have, when we multiply B and C together, we get 3 plus 0 and 1 plus 6 in the first column, 9 plus 0 and 3 plus 12 in the second column. That gives us the matrix 3, 7, 9, 15. Carrying out the multiplication, we get the matrix with columns 17, -34, 39, and -78. So, as promised, grouping either A and B together, then multiplying C, or grouping B and C together, then multiplying by A, gives us the same result. So in general, if A is an L by M matrix, B is an M by N matrix, and C is an N by P matrix, then A times B multiplied by C is the same thing as A multiplied by BC as L by P matrices. So if we assume that C has V1, V2, down to VP as its columns, where each of the V's are an n-dimensional vector, then we can form the product AB multiplied by C. The columns of this new matrix will be AB multiplied by V1, AB multiplied by V2, down to AB multiplied by VP. Now we use our result for vectors to shift our parentheses, and we recognize that this matrix can be thought of as the matrix A multiplied by the matrix with columns BV1, BV2, down to BVP. Now we recognize that the matrix we have written down on the right is simply B multiplied by C. And now we're done.